Okay, so here's a quick lesson on quantum numbers. So quantum numbers are just numbers. They all have numbers associated with them, but we won't learn all the numbers if you're wondering why they're called numbers. But basically, quantum numbers just tell you about the, sorry, I can't spell. They tell you where the electron's located. So they tell you about the position of the electron. So the first quantum number we're going to talk about is principal. So principal quantum number, we represent this with a lowercase n. So anytime we're talking about the principal quantum number, it will look like n equals 1, n equals 2, 3, and so forth. It can't be negative and it can't be 0. So n tells you the level. Actually, let me write this better. It's the energy level that the electron in question is in. So basically this means how far from nucleus. Man, I really can't spell today. Okay, so I went ahead and drew it for you so that we don't have to draw this a million times. But this kind of refers back to Bohr's model because Bohr was talking about the different energy levels. And so the principal quantum number is really just that simple. We're talking about which level. So as you see, the purple one is on like the first level. So for the purple ring, that would be like n equals 1. And then the second level would be like n equals 2. And then the third one would be 3, so that's n equals 3. So anytime we're talking about the second energy level, we would refer to it as n equals 2. Okay, so the next quantum number that we're going to talk about is the angular momentum. Angular momentum quantum number. So this one is represented by an L. And so I may have taught you in class or I may not have. There are numbers associated with this, but you don't have to know. So you don't have to know the numbers. All you need to know is that there are shapes. And that these shapes are symbolized by an S, a P, a D, and an F orbital. So that goes into what it actually means. So symbolizes, this is what it means. Okay. So the angular momentum is referring to the shape of the orbital. So you would think that it would all be circles, right? Because these are all circles, but that is actually not the case. They're not all circles, and I'm going to go on to the back of this page. I'm actually just going to slide down. And I'm going to draw all of the different shapes, the S, P, the D, and the F. So let's go down here. So angular momentum. Again, this is the shape. So we have an S, we have a, I'll just draw them down. We have an S orbital, we have a P orbital, we have a D orbital, and we have an F orbital. Okay, so the S stands for sphere. Man, I really can't spell. And so the S one's very simple. It's just a circle. Okay, but you have to picture it is in 3D. So it's not just like a circle, it's like a sphere. So I'm going to shade it so that you know it's like a sphere. Okay, the P orbital, this is, I refer to it as the infinity sign. I hope I spelled that right. And so if you lay it flat, then yes, it looks like an infinity sign. And again, this is kind of like shaded. If you stand it upright, it looks like a figure 8. I'm shading them just so you understand that these are areas and not just lines. Like they don't just follow these lines. They live in this space, okay? And then there's one more way, since this is all real life, it's 3D. So this is like coming out at you, and this one's going back out of the page. But again, oops. Again, let me shade it to let you understand. So if you were in class and listening, I talked about the X, Y, and Z axis. So we live in a 3D space, right? So we have the X axis, the Y axis, and then we have the Z axis that comes out at you. Let me use a different color. Okay, so all of these exist. And so when we turn this infinity sign on all the different axes, I can't say that word, then it looks different. So this one would be like the Y one, it's standing up, okay? This one would be like the X one because it's laying flat. And then this one is trying to come out at you, okay? So those are our three options for the P shape. So let's go back to, oops, I think this is my color. Let's go now moving down to the D shape. The D is a clover, okay? And I'm not going to draw all the different options. It's just double infinity signs. There are five total ways that you can draw this, okay? So here's 1, 2, 3, 4, 5. I drew an extra line. There are 5 total ways that you can draw the clover. I can't draw them, so there's no point in me trying. And then especially with the F orbital, I really can't draw this one. This is the double clover. So it is basically 2 of those D orbitals put on top of each other. Oh my, why did that happen? Sorry, let me try again. Okay, and so then I'm going to put another one. I'm outlining it so that it doesn't draw on top of it. Okay, and you're just going to have to trust me. There are 7 different ways of drawing it. So here's 1, and then there's 6 others. 1, 2, 3, 4, 5, 6, 7. Okay, so that is the angular momentum. So basically what we're saying is that they're not all these perfect circles, that they live in these different shapes like we've drawn down here. I really like the shading. Hold on. So basically, if I were going to include both the angular momentum and the principal quantum number together, let me draw what I mean. Let me erase this. This is not for you right now. So remember, the principal quantum number was discussing like which level you're at, if we're here, here, or here. And then the angular momentum is how we have all these different shapes, okay? So we are going to put these shapes together with the principal quantum numbers and show you how they all reach certain energy levels. So let me write in my nucleus, and then this will be my energy level 1, okay? So the purple is like N equals 1, and there's actually only a sphere here, so that's just the S orbital. Okay, for N equals 2, we're going to get a little further away. N equals 2, you have the S orbital and you have a P orbital. But for the P orbital, you have to have all 3 because all 3 exist. So what I drew was the S. This circle is the S. And then you have the P orbital that stands up straight, the P orbital that lies flat, and then you have the P orbital that's coming out at you. Okay? But do you see how they all reach this same level right here? They all reach this outer level because they all are at N equals 2. So we could go a step further and talk about N equals 3. So this one has a S, a P, and a D. So let me draw my S orbital. Okay, let me move it. I'm not very good at drawing. And then the P orbitals are just going to look the same, but they're bigger. I know this is getting all kinds of ugly. And then if I drew in my D orbitals, I mean, they are everywhere. So do you see how it's kind of like a cloud? But they do have these orbitals that they kind of orbit in. So they may stay like those electrons that live in this orbital may hover in like this specific section right here, okay? But they all reach the same energy level if they're at N equals 3. Okay, so how do we know which one of these orbitals it's in? How do we know if it's in that one or not? Okay, that is actually our next quantum number. That is going to be, let's use a different color. This is the magnetic. the magnetic quantum number, and it is associated with L, so it is M, and then it has a sub L because it's associated with L. So this tells you the orientation of the orbital. So again, I'm going to draw this down here. So basically, you see how I have 3 different orientations for P. I have 1, 2, 3, 4, 5 for D, 1, 2, 3, 4, 5, 6, 7 for F. And then up here with S, no matter which way you turn it, it only looks the same. So there are numbers associated with M sub L, and the numbers look like this. So that I could tell you like it's in the D orbital minus 2 M sub L. But again, you don't have to know these numbers. I'm just putting them in here so that you can understand the difference between M sub L and L. Okay, but what I need you to know is that there's only one option, one orbital for the S orbital. There's 3 for the P, and there's 5 for the D, and there's 7 for the F, okay? So M sub L would just tell you, if we cared about knowing this 0, if we cared about knowing this 0, 0, -1, +1, which you may in your life if you continue in chemistry, but if we cared about that, that would be with this magnetic quantum number, okay? So this quantum number tells you exactly which orbital we're in, but we won't ever work too far into this one, okay? So the last one, and probably the easiest one, is the spin quantum number. So this one is kind of its own thing, but it's still M, and then it has sub S. I don't really know why the M part is there. But this is how you're representing the spin quantum number. So this one, it's very simple. It just tells you the spin of the electron. So let me explain what I mean. So electrons will come into these orbitals. So 2 electrons can fit each line. Okay, so there's 2 that can fit each of these orbitals. Okay, but when they pair up and go into this orbital, they will have opposing spins. So if this is my electron, this one may spin this way, and the other one may spin the other direction, okay? So they will pair up together and fit into that orbital, okay? But when they do, they have opposing spins. So back up here to like the draw part. If we're symbolizing it by a number, we say +1/2 and -1/2, because together that makes 0. But when we're actually drawing it, we draw half an arrow up for the +1/2 and half an arrow down. So when we actually put it into the problem down here, let me get rid of all this ugly stuff. When we actually put it into our shells, we draw 1 up, 1 down. And so these arrows, each arrow represents an electron, okay? And so the reason that it's half an arrow is because over here the value was +1/2 and -1/2. So it's half that arrow, okay? So when we put them in here, we would put them all the way across and then pair them up. And they pair, spin up, spin down. Okay, so that's all you need to know about the quantum numbers. So I just want you to be familiar with what they all are. And this leads us into our electron configuration lecture, which is next, where we talk about specifically where the electrons are. Okay.